This is problem number 4, and it really shines a light on one of the challenges with exam FM is you have lots of very similar looking interrelated formulas and relationships that it's going to take some time to get a handle on. So I've written out all the formulas we're going to need to solve this particular problem. So we have this perpetuity that costs 77.1. It makes end of year payments. And then it's got this interesting payment structure where it pays $1 or 1 at the end of year 2, 2 at the end of year 3, and so on and so forth until we get to some value n, where it then just pays n constantly for every given year after that. So what we really have here for this perpetuity is an increasing annuity followed by a perpetuity. So the first thing I'm going to do is simplify this structure, right? I wrote out everything we would need here, but we don't make any payments at the end of the first year, so that term isn't needed. So I'm going to rewrite just as v squared plus 2v to the third, maybe we'll do one more, plus 3v to the fourth, and then that will go on until we get to some value n, and then we will pay n constantly for each subsequent year all the way out until the end of time. So this looks a lot like an increasing annuity, but there's a little bit of an offset, right? We are paying 1 at the end of year 2, 2 at the end of year 3, 3 at the end of year 4. So what I'm going to do is I'm going to factor out a v, that is my present value factor. I'm going to factor that out of the entire chain. It's a little bit different than what the answer key does, but the results are going to be the same. So we factor out the v. Now we have v plus 2v squared plus 3v to the third, and so on and so forth until we get to n times v to the n, and then we go on from there. So now we do have an increasing annuity. We have the increasing annuity here, and then the perpetuity, the constant perpetuity here. So I'm going to rewrite this with my annuity symbols. One thing to keep in mind when solving these problems is you want to wait kind of till the very end before you start plugging in values for v and I and d. It just makes it easier to work out and to write out all the steps of your problem. So 77.1 will be equal to v times my increasing annuity, which is given by this formula here, which has an annuity due baked into it. So there's my increasing annuity, and then I'm going to add on my constant perpetuity. But the thing is, this perpetuity, we're going to pay n dollars for said perpetuity, and then we're going to have to discount it back to the beginning, because if our price is 77.1, that's the present value of the annuity. So we're going to have to discount the perpetuity back. Okay, and that should do it. Increasing annuity plus perpetuity. Increasing annuity plus perpetuity. All right. So the first thing I'm going to do is separate this term right here, because we're going to get a nice cancellation. 77.1 equals v times a double dot over n of n over I minus n times v to the n over I plus n times v to the n over I. So these terms cancel, and really that's a very good sign if you get a nice cancellation like that you're on the right track. So rewriting, we've got 77.1 equals v times a double dot n over I. And I'm just going to isolate this annuity symbol by dividing both sides by v and multiplying both sides by I. Let's kind of do that over here. 77.1 divided by v times I equals a double dot n. But of course, this annuity due can be rewritten as such. So let's do that. Instead of writing the annuity symbol, let's see. This should be an I, not a T. There we go. So rewriting 1 minus v to the n over d. And then again, I'm just going to keep collecting constant values on this side of the equation because d, v, and I are all known to us. We just haven't substituted in the value yet. So let's multiply both sides by d, and we get 77.1 times I times d divided by v equals 1 minus v to the n. And while we could keep going here, at this point, I am ready to convert this into a single value. So if we go to our calculator and we do 77.1 times I times d over v, we're going to get something that is just about 0.85 equals 1 minus v to the n. But of course, we know v is 0.905 to the n. So now we're getting close because we're looking for here, what we were asked for was the constant n. We have all these other variables, but they're not really variables. They're known to us. We've just written them. We've kept them in their letter form until this step right here. But this value of n is not known to us. So that's what we want to solve for. So let's subtract 1 from both sides and then multiply both sides by -1 to get 0.15 equals 0.905 n. You can take the natural log of both sides. We get the natural log of 0.15 equals, applying the rules of logarithms, n times the natural log of 0.905. I'm just going to come up here for the sake of space. Again, not going to simplify these values until the very end. It's just much easier to keep things in this form than it is to go out and create a decimal with 6 digits or whatever. So, dividing both sides by the natural log of 0.905, we get the natural log of 0.15 over the natural log of 0.905 is equal to n. And now, finally, we can go to the calculator, and if you put this expression in, you get that n is just about 19.